Look up at the night sky, really look, and tell me what you see. A scattering of stars, perhaps the faint glow of distant galaxies, or the steady arc of a passing satellite. But beneath that quiet beauty lies a mystery so vast, so profound, it's humbled thinkers, scientists, and dreamers for millennia. The cosmos doesn't just stretch beyond our vision, it defies our understanding. We've mapped planets, unraveled the physics of black holes, even glimpsed the afterglow of the Big Bang itself. And yet, for every question answered, the universe whispers 10 more. What flickers in the darkness between galaxies? Are we truly alone, or is something or someone watching from the shadows? This isn't just about science. This is about the uncharted territories where logic meets legend, where data dances with the unknown. Welcome to Mysteries Illuminated, a journey beyond the scientific lens into the heart of space. Think of the greatest explorers in history, the ones who sailed past the edge of the map, who stared into the abyss and asked, "What's out there?" That same fire burns today, but our frontier isn't oceans or continents. It's the cosmic ocean, where nebulae swirl like tempests and planets orbit stars we'll never touch. Science gives us tools, equations, theories, but some truths resist even the sharpest microscope or the most powerful telescope. Why do galaxies spin faster than they should? What lurks in the eerie silence of the Hubble Deep Field, where ancient light holds secrets older than time? These aren't just puzzles for astronomers, they're invitations to wonder, to imagine, to step beyond what we think we know. So let's begin where the textbooks leave off. This isn't a lecture, it's an expedition. Together, we'll traverse the edges of discovery where the line between fact and mystery blurs. We'll meet the phenomena that defy explanation, the cosmic riddles that keep scientists awake at night, and the whispers from deep space that challenge everything we assume about reality. By the end, you won't just see the stars differently, you'll feel them, because the universe isn't just a place, it's a story, and you're about to become part of it. Picture a jigsaw puzzle spread across a table, only this puzzle has no edges, no box to show you the final image, and half the pieces are invisible. That's the universe as we know it. Every breakthrough in astronomy, every new telescope we launch, reveals another handful of pieces, but the bigger picture, it's still emerging from the shadows. Take dark matter, for instance. We can't see it, can't touch it, yet we know it's there because galaxies spin as if gripped by some unseen hand. Nobel laureate physicist Adam Rees once called it the universe's most stubborn secret, a ghostly presence that outnumbers ordinary matter 5-1, yet slips through our detectors like smoke. Then there are black holes, those cosmic paradoxes where gravity becomes so strong that not even light can escape. Einstein's equations predicted them over a century ago, but we're only now scratching the surface of their secrets. Why do some hum with energy, spewing jets of plasma across galaxies, while others sit in eerie silence? Event Horizon Telescope director Shepard Doleman compares studying them to trying to read a newspaper from the moon while it's on fire. And even with our sharpest tools, we've barely glimpsed their true nature. But perhaps the most haunting mystery is the sheer scale of what we don't know. The Hubble Deep Field image, a snapshot of a patch of sky no bigger than a grain of sand held at arm's length, revealed thousands of galaxies, each with billions of stars. Multiply that across the entire cosmos, and the numbers become meaningless to the human brain. Astronomer Carl Sagan put it best: the universe is a pretty big place. If it's just us, seems like an awful waste of space. Yet after decades of listening, the silence from the void remains unbroken. No signals, no signs, just the quiet hum of the cosmic microwave background, the afterglow of creation itself. Here's the twist: some of these puzzles might never fit neatly into our textbooks. Dark energy, the force accelerating the universe's expansion, behaves like nothing in our current physics. It's as if the cosmos is rewriting its own rules as we watch. Maybe that's the real lesson, not that we're failing to solve the puzzle, but that the puzzle is far stranger, far grander than we ever imagined. And that's where the real adventure begins. Imagine holding a snow globe, only instead of tiny flakes swirling in water, it's an entire galaxy spinning in the void. Now here's the catch: what you see is just the glitter. The real weight, the force keeping everything from flying apart, is invisible. That's dark matter in a nutshell. It's the universe's hidden scaffolding, outweighing ordinary matter 5 to 1, yet it leaves no trace, no light, no heat, no shadow. We only know it's there because galaxies rotate like carnival rides without enough gravity to hold them together. Unless something unseen is gripping the reins, scientists have spent decades chasing this ghost. Some think dark matter could be WIMP, weakly interacting massive particles, hypothetical heavyweights that barely touch normal matter, like strangers passing in a crowd. Others bet on actions, particles so lightweight they'd slip through detectors like whispers through a wall. Then there are the wilder ideas. What if dark matter isn't a particle at all, but a flaw in gravity itself? Or a cosmic echo from another dimension, bleeding into ours, the most unsettling possibility. We might be missing something fundamental, like fish trying to understand rain. The hunt isn't just philosophical. Deep underground, in labs shielded from cosmic noise, detectors wait for a single bump, a ping from a dark matter particle. In space, telescopes map the distorted light of distant galaxies, tracing the gravitational fingerprints of the invisible. So far, silence, but every null result tightens the noose, forcing us to rethink. Maybe dark matter isn't one thing but many, a zoo of particles, each stranger than the last. Or perhaps, as some theorists suggest, it's a signpost pointing to realities beyond our own, where the rules of physics rewrite themselves. Here's what keeps astronomers up at night. Dark matter isn't just a missing piece. It's the glue holding the cosmic puzzle together. Without it, galaxies would never have formed, stars wouldn't ignite, and we wouldn't be here to wonder. Yet after 80 years of searching, it remains the universe's ultimate sleight of hand, a reminder that sometimes the most powerful forces are the ones we can't see. And that's the real magic of science, not the answers we find, but the mysteries that refuse to be solved. Black holes aren't just cosmic vacuum cleaners, they're the universe's most enigmatic paradoxes, places where gravity wins the ultimate tug of war. Imagine a whirlpool so powerful that nothing, not even light, can swim against its current. That's the event horizon, the point of no return. In 2019, humanity caught its first glimpse of one, a fiery ring of light framing an abyss, captured by the Event Horizon Telescope. That image of the supermassive black hole in galaxy M87 wasn't just a scientific triumph, it was a wake-up call. Here was a monster weighing 6.5 billion times more than our sun, bending space-time like a bowling ball on a trampoline. But the real mystery lies deeper, literally. At the heart of every black hole sits a singularity, a point where density becomes infinite and the laws of physics, well, they quit. Time slows to a crawl here, warped so severely that a single minute near the edge could stretch into years for someone watching from afar. It's like stepping into a science fiction novel, except the science is very real. Stephen Hawking shook the world when he theorized that black holes aren't entirely black. They leak. Tiny particles, now called Hawking radiation, slowly evaporate over eons, as if the universe itself is whispering secrets. Now here's where it gets wild. Some physicists speculate that black holes might not be dead ends at all, but gateways. Could a singularity punch through space-time like a needle through fabric, stitching together distant points in the cosmos? Einstein's equations allow for it, at least on paper. The idea of black holes as portals isn't just fantasy. It's a fringe but serious thread in theoretical physics. Of course, stepping through one would be messy. The tidal forces would stretch you into a human noodle long before you reached the other side, assuming there is one. Yet the question lingers, what lies beyond the horizon? A new universe, a mirrored version of our own, or simply oblivion? These aren't just thought experiments. They're challenges to our understanding of reality itself. Because if black holes teach us anything, it's that the universe loves a good plot twist, and the next chapter might rewrite everything we think we know. What if the universe had secret passageways, cosmic backdoors that could whisk you across galaxies in the blink of an eye? That's the promise of wormholes, hypothetical tunnels through the fabric of space-time that have tantalized scientists and sci-fi fans alike. The math behind them traces back to 1935, when physicists Albert Einstein and Nathan Rosen stumbled upon a strange solution to the equations of general relativity. These so-called Einstein-Rosen bridges suggested that black holes might not be dead ends, but rather doorways, connected to another point in space by a throat-like tunnel. Picture folding a piece of paper so two dots touch, then poking a hole through. That's the essence of a wormhole, a shortcut through the cosmic sprawl. But here's the catch. The wormholes predicted by Einstein's equations would snap shut instantly, crushed by their own gravitational forces before anything could pass through. To stay open, they'd need something exotic like negative energy, a theoretical substance that repels gravity instead of attracting it. Think of it like trying to prop open a collapsing tunnel with anti-gravity scaffolding. While no one's ever detected negative energy, quantum physics hints that it might exist in tiny amounts, flickering in and out of existence at the subatomic level. Could we somehow harvest enough to stabilize a wormhole? That's the million-dollar question, one that's fueled everything from blockbuster movies like Interstellar to cutting-edge research at institutions like Caltech. The implications are staggering. A traversable wormhole could revolutionize space travel, turning a journey of thousands of years into a leisurely stroll. Imagine stepping through a portal near Earth and emerging near Alpha Centauri, or even another galaxy entirely. But before we pack our bags, there's a mountain of hurdles. Wormholes, if they exist, would likely be microscopic, smaller than an atom. Scaling one up to human size would require engineering beyond our wildest dreams, not to mention the risk of cosmic radiation or the tunnel collapsing mid-trip. And then there's the ultimate irony. Even if we built one, we might not control where it leads. The other end could open anywhere, anytime, even in the distant past or far future. So are wormholes real, or just a beautiful quirk of mathematics? The truth is, we don't know. Some physicists argue they're mere artifacts of equations, like shadows cast by a deeper truth we haven't grasped yet. Others believe they're out there, hidden in the folds of the universe, waiting to be found. Either way, wormholes remind us that space-time isn't just a static stage. It's a dynamic, twistable fabric, full of possibilities we're only beginning to explore. And that's the real magic, not just the answers we seek, but the questions that keep us reaching for the stars. The universe is unimaginably vast, home to hundreds of billions of galaxies, each with billions of stars, most likely orbited by countless planets. With numbers like these, the odds seem overwhelmingly in favor of life existing elsewhere. So why haven't we heard a single whisper from the cosmos? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common, why does the universe feel so eerily empty? One chilling answer is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. Maybe the filter is behind us, something rare and miraculous that allowed life to emerge on Earth against impossible odds. Or worse, it could lie ahead, a catastrophic event, like self-destruction through war or environmental collapse, that snuffs out civilizations before they can spread. The unsettling truth: we don't know which side of the filter we're on. Others propose gentler explanations. The zoo hypothesis suggests advanced civilizations know we're here but choose to observe us quietly, like scientists watching animals in a preserve. Or perhaps intelligent life is simply rarer than we think, buried under ice-covered oceans, or snuffed out by cosmic disasters before it can reach out. Even our own efforts, like SETI, decades of scanning the skies for radio signals, have turned up nothing but static. Yet recent discoveries keep the hope alive. Thousands of exoplanets, worlds orbiting distant stars, have been identified, some in the so-called Goldilocks zone, where conditions might be just right for life. But finding a planet is one thing, finding a neighbor is another. Are we alone, or are we like ants in a vast forest, unaware of the hikers passing just overhead? This mystery spills into another, the fleeting glimpses of UFOs, or as scientists now call them, UAPs, identified aerial phenomena. Are these misidentified aircraft natural phenomena, or something far stranger? The line between science and speculation blurs here, but one thing's certain: the universe is full of questions we're only beginning to ask, and the answers, when they come, might rewrite our place in the cosmos. For decades, UFOs, now rebranded by scientists as UAPs, lived on the fringes of serious discussion, dismissed as the stuff of conspiracy theories and blurry nighttime photos. But something shifted in recent years. Suddenly, the US government began releasing videos captured by military pilots, footage showing objects moving in ways that defy our understanding of physics. Take the now famous Tic Tac incident from 2004, when Navy pilots off the coast of San Diego encountered a smooth, oblong object with no visible wings or exhaust. It darted at hypersonic speeds, made instantaneous 90-degree turns, and vanished before their eyes. Radar operators confirmed it wasn't a glitch. This wasn't grainy footage from a desert highway. This was data from the world's most advanced tracking systems. So what are we dealing with? The possibilities split into two camps, the mundane and the extraordinary. On one hand, many UAPs turn out to be weather balloons, drones, or atmospheric phenomena like ball lightning. Even military tech can be misidentified. Think of stealth aircraft testing in the 1980s that spawned countless UFO reports. But then there are the outliers, the cases that resist easy explanation. Objects accelerating from 0 to thousands of miles per hour without sonic booms. Craft hovering motionless in hurricane-force winds. The Pentagon's own 2021 report admitted that dozens of these incidents remain unidentified, with no clear link to human technology or natural causes. That raises the billion-dollar question: if some UAPs aren't ours, whose are they? The extraterrestrial hypothesis is the elephant in the room, but it's not the only one. Some theorists suggest these could be ultra-secret projects, next-gen drones or propulsion systems developed by rival nations. Others float even wilder ideas, like ancient civilizations surviving in hidden pockets of Earth, or interdimensional visitors slipping into our reality like shadows through a curtain. The truth is, we lack the data to say for sure, but here's what's undeniable: the stigma around this topic is crumbling. NASA now has a UAP research team. Congress holds hearings. Even former skeptics like astrophysicist Neil deGrasse Tyson admit the phenomena deserve rigorous study. Perhaps the most intriguing clue lies in the patterns. UAP sightings cluster around nuclear facilities and military exercises, as if whatever's behind them is intensely curious or concerned about our technological leaps. Whether it's advanced surveillance or something far stranger, one thing's clear: the skies hold mysteries we're only beginning to acknowledge. And as we peel back the layers, we might find that reality is far more fluid and far more fascinating than we ever imagined. One moment the cosmos is quiet, the next a flash of radio energy brighter than a billion suns erupts from the void, then vanishes, leaving astronomers scrambling. These are fast radio bursts, or FRB, cosmic firecrackers that last just milliseconds but pack more energy than our sun emits in 80 years. First detected in 2007, these bursts arrive without warning, often from galaxies billions of light years away. Some explode once and disappear forever. Others, like the infamous repeater FRB-1212, fire off signals like clockwork, pulsing across the universe with eerie precision. So what's blasting these signals? The leading suspect is Magneta's super-dense, highly magnetized neutron stars that occasionally unleash violent flares. Picture a spinning top wrapped in a magnetic field so intense it warps reality itself. When these cosmic powerhouses quake or snap, they might release bursts powerful enough to reach us across unimaginable distances. But not all FRBs fit this mold. Some arrive in patterns too regular, too deliberate seeming. Could we be hearing the distant hum of alien engineering? It's a fringe theory, but not impossible. Advanced civilizations might use focused radio beams to propel light sails across galaxies, leaking flashes detectable across the universe. Then there's the mystery of localization. Most FRBs come from impossibly far away, but in 2020, astronomers caught one erupting inside our Milky Way. That proximity gave scientists their clearest look yet the data only deepened the puzzle. The burst was laced with strange, twisted radio waves, evidence of extreme magnetic fields, yes, but also hints of environments unlike anything we've seen. It's as if the universe keeps handing us pieces to a puzzle we don't yet know how to assemble. The real intrigue lies in what FRBs could reveal. Their signals twist and distort as they traverse the cosmos, picking up traces of the invisible matter between galaxies. By studying these distortions, astronomers have mapped the universe's missing matter, the diffuse gas too faint to see directly. FRBs might even help measure the expansion rate of the cosmos, offering clues to dark energy's grip on reality. But the question lingers: are these bursts cosmic accidents or something more? The repeating signals, with their tantalizing rhythms, force us to wonder. Nature rarely repeats without reason. Whether it's magnetas screaming into the void or something far stranger, FRBs remind us that the universe is still writing its rulebook, and we've barely turned the first page. For over 60 years, scientists have been straining to hear a single note in the cosmic silence, a signal, a whisper, anything that might prove we're not alone. This is the mission of SETI, the search for extraterrestrial intelligence, and it began with a simple premise: if advanced civilizations exist, they might be broadcasting their presence across the galaxy. The earliest efforts relied on radio telescopes, massive dishes tuned to the universe's natural radio chatter, listening for deliberate patterns hidden in the noise. It's like standing in a crowded room, ears straining for someone calling your name in a language you don't yet understand. Then came the wow signal. On August 15, 1977, a radio telescope in Ohio picked up a burst so powerful, so unnatural, that astronomer Jerry Ranson circled it on the printout and scribbled, "Wow." In the margin, lasting 72 seconds, the signal came from the direction of the constellation Sagittarius and matched the exact frequency hydrogen emits in space, a logical choice for an alien hello. But when scientists turned their telescopes back to the spot, they heard only silence. Was it a fleeting transmission, a cosmic flare, or something else? Decades later, the WOW signal remains the closest we've come to a potential alien message, a tantalizing maybe that refuses to be solved. But SETI isn't just about radio waves anymore. As technology evolves, so do the ways we search. Optical SETI now scans the skies for laser pulses, brief, focused flashes that could be interstellar lighthouses. Meanwhile, the hunt for technosignatures looks for evidence of alien engineering, like massive megastructures orbiting distant stars or industrial pollution in exoplanet atmospheres. Imagine spotting the glow of city lights on a planet light years away, or catching the chemical fingerprint of a civilization burning fossil fuels. These aren't sci-fi fantasies, they're real strategies backed by telescopes like James Webb, which can analyze the air of distant worlds for biosignatures like oxygen or methane, hints that life, even if not intelligent, might be breathing out there. Yet here's the irony: what if we're listening for the wrong things? Our searchers assume aliens think like us, using technologies we recognize. But a civilization a million years ahead might communicate in ways we can't yet detect: quantum entanglement, neutrino beams, or something beyond our physics. Or perhaps they've moved beyond physical signals entirely, leaving behind artifacts or encoded messages in the fabric of space-time itself. This uncertainty is baked into the Drake equation, the famous formula estimating the number of detectable civilizations in our galaxy. Plug in hopeful numbers and the Milky Way could be buzzing with life. Use conservative ones and we might be utterly alone. The equation isn't an answer, it's a mirror reflecting how much we still don't know. And that's the heart of SETI gamble. Every silent night sky is either a testament to our solitude or proof that we're still learning how to listen. The search continues, not because we're sure of what we'll find, but because the question itself, are we alone, is too profound to leave unanswered. In 1961, astronomer Frank Drake scribbled an equation on a blackboard, not to solve a problem, but to frame one. The Drake equation wasn't designed for precise answers. It was a thought experiment, a way to quantify the unquantifiable, the likelihood of intelligent life beyond Earth. At first glance, it looks deceptively simple, a string of variables multiplied together, each representing a cosmic hurdle life must clear to announce its existence. But peer closer and you'll find a universe of uncertainty hiding in every term. Start with the basics. How many stars are born each year in our galaxy? That's the first variable, our star. Current estimates suggest the Milky Way spawns about 7 new stars annually, but how many of those stars host planets? Thanks to telescopes like Kepler, we now know planets outnumber stars, with billions potentially orbiting in habitable zones. That's the second and third variables, F sub p and N sub e planets per star, and those ripe for life. Optimists argue 1 in 5 Sun-like stars might cradle an Earth-like world. Pessimists counter that habitable doesn't mean inhabited after all. Venus and Mars technically sit in our solar system's Goldilocks zone, yet neither hosts liquid water or thriving ecosystems today. Then comes the great leap. How often does life emerge on suitable planets? Here, the equation veers into speculation. On Earth, life appeared almost as soon as conditions allowed, a hint that biology might ignite easily given the right chemistry. But without another example, F sub L remains a guess. Some say life could be as common as weeds. Others argue we might be a fluke, a 1 in a trillion stroke of luck. And even if life starts, how often does it evolve intelligence? That's F sub I, a variable haunted by Earth's own history. Dinosaurs ruled for over 100 million years without inventing radio telescopes. Intelligence isn't an inevitable endpoint. It might be a cosmic roll of the dice. Now, the most haunting variable, L, the average lifespan of a communicating civilization. This is where the equation turns philosophical. Imagine a species reaches our technological level, how long before it self-destructs through war, environmental collapse, or simply loses interest in the stars? If civilizations typically last only a few centuries, the galaxy might be littered with silent ruins. But if even a handful endure for millions of years, the cosmos could hum with voices. Plug in optimistic numbers, and the Milky Way might host thousands of civilizations at this very moment. Use conservative ones, and we could be the only one in this epoch. But here's the twist. The Drake equation assumes life follows rules we understand. What if it doesn't? Silicon-based life, plasma beings in nebulas, or sentient AI lurking in data streams, our imagination might be too limited to even frame the right questions. The equation also silently assumes civilizations want to be found. Yet a truly advanced species might regard noisy newcomers like us with caution, choosing silence over contact. Or perhaps they've moved beyond radio waves, communicating in ways invisible to our primitive instruments. Ultimately, the Drake equation's power isn't in its math, it's in the conversations it sparks. Every term is a doorway to deeper mysteries, a reminder that the universe owes us no answers. But as we refine each variable, counting exoplanets, probing Mars for microbes, listening for cosmic hellos, we're not just calculating odds. We're deciding what kind of universe we live in, one brimming with neighbors or one where, for now, we're the only ones telling stories under these stars. Either way, the search itself changes us, because to look for life is to wrestle with what it means to be alive. What if life on Earth didn't actually begin here? Picture a comet, icy and ancient, drifting through the void, locked inside its frozen core, not just water or minerals, but the raw ingredients of life itself. This is Panspermia, the bold idea that life might hitchhike across the cosmos, seeding planets like a cosmic gardener scattering dust, and the evidence. It's stranger than fiction. Take Extremophiles, Earth's toughest life forms. These microscopic survivors thrive in places that would kill almost anything else. Boiling hydrothermal vents, acidic lakes, even the vacuum of space. In 2008, scientists strapped bacteria to the outside of the International Space Station. After 18 months of brutal radiation and freezing temperatures, some still woke up when brought back inside. If microbes can endure space, could they have ridden a meteorite to Earth billions of years ago? Then there are the meteorites themselves. In 1969, the Murchison meteorite crashed into Australia, carrying a stunning payload, over 90 different amino acids, the building blocks of proteins. Even more intriguing, some of these molecules were left-handed, a mirror image arrangement common in Earth's biology but rare in random chemistry. Coincidence? Or a clue that life's ingredients were delivered ready-made, like a cosmic care package? But Panspermia raises bigger questions. If life can hop between worlds, does that mean the universe is designed for it? Consider the eerie fine-tuning of physical constants. If gravity were slightly stronger, stars would burn out too fast. If the electromagnetic force were weaker, atoms wouldn't bond. It's as if the cosmos is calibrated just right for life to emerge and perhaps spread. Some theorists speculate this isn't luck, but evidence of a deeper architecture, with life woven into the fabric of reality itself. Yet the mystery deepens. Even if life traveled here, where did it start? A warm pond on Mars, blasted into space by an asteroid impact. The icy oceans of Europa, ejected by a cryovolcano. Or somewhere impossibly distant, a world we'll never see. Panspermia doesn't answer life's ultimate origin, it just stretches the puzzle across the stars. And that's the real allure, not just wondering if we're alone, but whether we're all travelers on the same cosmic journey. Imagine tweaking the dials of reality just slightly: the strength of gravity, the charge of an electron, the nuclear forces holding atoms together. Change any one of these constants by a hair, and the universe as we know it collapses into chaos. Stars wouldn't form, carbon, the backbone of life, wouldn't exist. Even water, that magical solvent essential for biology, would lose its unique properties, the odds of all these numbers lining up perfectly by chance. Astronomer Fred Hoyle once said it's like tossing a deck of cards into the air and watching them land in perfect numerical order. Yet here we are in a cosmos that seems custom-built for life. This eerie precision is what physicists call the fine-tuning problem. Take the cosmological constant, the value governing the expansion of the universe. If it were slightly larger, matter would fly apart too fast for galaxies to coalesce. Slightly smaller, and everything would collapse back into a cosmic crunch. The acceptable range for this number is vanishingly narrow, like balancing a pencil on its tip in a hurricane. Nobel laureate Steven Weinberg called it the most striking coincidence in all of science. But is it really a coincidence? Enter the anthropic principle, the idea that the universe must be compatible with life, because otherwise we wouldn't be here to observe it. In other words, we're not seeing a designed universe, we're seeing the only kind of universe where observers could exist. It's a bit like a lottery winner marveling at their odds, forgetting that someone had to win. But this explanation leaves many scientists unsatisfied. Philosopher Nick Bostrom compares it to a firing squad of 100 sharpshooters all missing you by accident. Possible technically, plausible, that's another question. That's where the multiverse theory comes in. If our universe is just one bubble in an endless froth of universes, each with different physical laws, then of course we'd find ourselves in the one where life is possible. The others, they'd be barren, lifeless, with no one to wonder why. Harvard physicist Lisa Randall likens it to walking into a clothing store. You're not shocked to find a shirt that fits you because you'd never pick one that didn't. But here's the catch: the multiverse is still speculative, a theoretical safety net that can't yet be tested. Not everyone buys these explanations. Some, like physicist Paul Davies, argue that fine-tuning hints at something deeper, a universe with purpose, or even a law of laws we haven't discovered yet. Others, like cosmologist George Ellis, suggest we might be asking the wrong questions altogether. What if the constants aren't arbitrary dials but interconnected parts of a grander structure, like notes in a symphony we're only beginning to hear? At the heart of this debate lies a humbling truth: the universe doesn't owe us answers. Its mysteries might transcend our tools, our math, even our capacity to understand. Whether through multiverses, deeper physics, or something beyond our current imagination, one thing's certain: the cosmos is stranger, more intricate, and more wondrous than we've yet dared to dream. And that, perhaps, is the greatest mystery of all. At the smallest scales of the universe, reality behaves in ways that defy common sense: particles existing in multiple places at once, objects changing behavior when observed, and distant particles whispering to each other faster than light should allow. This is the quantum realm, a domain so bizarre that Einstein famously called its phenomena spooky action at a distance. But what if these microscopic quirks aren't just laboratory curiosities? What if they're woven into the very fabric of space itself, influencing everything from black holes to the birth of stars? Take quantum entanglement, for instance. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are, even if one's on Earth and the other near a distant galaxy. Experiments have confirmed this happens faster than light, seemingly violating relativity's cosmic speed limit. Some theorists, like physicist Juan Maldacena, speculate that entanglement might be the hidden glue connecting space-time itself, with every particle subtly linked across the universe like threads in a vast, invisible tapestry. Could this phenomenon explain how black holes transfer information, or why the cosmos appears so finely tuned? The holographic principle even suggests our three-dimensional reality might be a projection of entangled quantum data stored on a two-dimensional surface at the universe's edge, a concept that sounds like science fiction but emerges straight from the math. Then there's the observer effect, the strange truth that quantum systems only settle into definite states when measured. Some, like physicist Roger Penrose, propose this isn't just a quirk of tiny particles but a clue to something grander, that consciousness itself might play a role in shaping reality. His orchestrated objective reduction theory suggests quantum processes in the brain's neurons could bridge the gap between mind and cosmos, implying the universe might not just contain observers but require them to exist. It's a controversial idea, but one that blurs the line between physics and philosophy, hinting that the cosmos could be far more participatory than we ever imagined. Now consider time, a concept that feels solid in daily life but dissolves into uncertainty at quantum scales. Particles can exist in superpositions of time just as they do in space, and quantum time crystals exhibit motion without energy, forever oscillating in a weird, perpetual dance. Could these phenomena hold keys to understanding time's arrow, or even the possibility of traversing it? Experiments with entangled particles already suggest that causality, the bedrock of time's flow, might be more flexible than we thought. If quantum effects scale up to cosmic levels, as some string theorists propose, the universe might not just have mysteries, it might be one, a vast, shimmering question mark written in the language of probabilities. From the way galaxies align in unexpected patterns to the eerie silence of the cosmic void, quantum mechanics might be the Rosetta Stone we've been missing. It's a reminder that the universe doesn't owe us intuitive explanations, and that the deepest truths often lie where logic ends and wonder begins. Pick up a glass and let it slip from your fingers. Watch it shatter on the floor. Now try to imagine the reverse, the shards leaping back into your hand, reassembling perfectly. That never happens, and the reason isn't just about gravity or physics. It's about entropy, the universe's hidden rulebook dictating why time only marches forward. At its core, entropy measures disorder, and the second law of thermodynamics states it always increases in closed systems. Scrambled eggs don't unscramble themselves. Ice melts in warm rooms but never spontaneously refreezes. Every irreversible process, every moment that feels like time passing is entropy in action, dragging the universe toward chaos. Yet here's the paradox: the equations governing physics don't care about time's direction. Newton's laws, Einstein's relativity, even quantum mechanics work just as well if time runs backward. The math is timeless, so why does our lived experience arrow forward? One compelling answer lies in the Big Bang. The early universe was a hot, dense soup of particles in near-perfect order, a state of astonishingly low entropy. As it expanded and cooled, that order unraveled, creating the gradient that drives time's flow. Think of it like a wound-up spring slowly unwinding, powering the cosmic clock. But this raises a deeper question. Why was the universe's starting point so exquisitely ordered to begin with? Some theorists, like Sean Carroll, suggest our universe might be one bubble in a vast multiverse, where fluctuations occasionally spawn low-entropy regions like ours. Others propose cyclical models where a collapsing universe bounces into a new Big Bang, resetting entropy in the process. The ekpyrotic theory imagines our cosmos as one membrane colliding with another in higher dimensional space, igniting expansion while erasing the thermodynamic past. Then there's eternal inflation, where pocket universes endlessly bud off an inflating multiverse, each with its own arrow of time pointing in random directions. In such a cosmos, we'd inevitably find ourselves in a universe where time aligns with increasing entropy, because conscious observers couldn't exist otherwise. But what if time itself is an illusion? Quantum gravity approaches like loop quantum relativity suggest time might emerge from more fundamental, timeless processes, like temperature emerging from the motion of molecules. In this view, the flow of time could be a cosmic sleight of hand, a side effect of our limited perception. Even the distinction between past, present, and future might be, as Einstein put it, a stubbornly persistent illusion. This brings us to the ultimate mystery, the universe's origin. If time began with the Big Bang, asking what came before might be meaningless, like asking what's north of the North Pole. Yet quantum mechanics hints at possibilities. In a vacuum, particles flicker in and out of existence, borrowing energy from nothingness. Could the universe have done the same? Some models, like Hartle-Hawking's no-boundary proposal, describe a self-contained cosmos without a singular beginning, where time smoothly transitions from an imaginary dimension at the quantum level. Others imagine a cosmic hologram, with our four-dimensional reality projected from information encoded on a distant boundary. The deeper we dig, the stranger the questions become. Is time fundamental or just a useful fiction? Does entropy sculpt reality, or is it a shadow cast by something deeper? The answers, if they exist, might lie beyond the edge of physics as we know it, in a realm where time, space, and causality dissolve into something far more mysterious. And that's the true wonder, not just the mysteries we've uncovered, but the ones waiting to rewrite the very questions we ask. The Big Bang Theory is the most well-supported explanation for the origins of our universe, but it doesn't begin with a bang at all. Instead, it starts with a question mark. We know the cosmos expanded from an unfathomably hot, dense state around 13.8 billion years ago. The evidence is etched into the heavens, galaxies racing away from each other, the afterglow of the cosmic microwave background, the precise ratios of light elements like hydrogen and helium. Yet for all its predictive power, the Big Bang Theory leaves one gaping hole: what set it in motion. What, if anything, came before? One possibility lies in the quantum foam, the seething turbulence of empty space at the smallest scales. Even in a perfect vacuum, particles flicker in and out of existence, borrowing energy from nothingness before vanishing again. Could the universe itself have emerged from such a fluctuation? In this scenario, our cosmos might be a bubble of stability in an infinite quantum sea, where universes pop into being like bubbles in boiling water. Nobel laureate Roger Penrose takes this idea further with his conformal cyclic cosmology, suggesting that the Big Bang wasn't a true beginning but a reset, a rebound from the distant future of a previous universe where all matter has decayed into radiation and time loses meaning. Then there's string theory's wilder proposition, the collision of higher dimensional membranes, or brains, floating in a vast multiverse. Picture two sheets of paper drifting in a breeze until they smack together. That impact could have unleashed the energy of a Big Bang. This ekpyrotic universe model implies our cosmos isn't unique, just one episode in an eternal cycle of collisions. Meanwhile, the no-boundary proposal by James Hartle and Stephen Hawking erases the need for a beginning entirely. describing a universe that smoothly curves from space into imaginary time at the quantum level, like a globe with no edge. Yet the most haunting clue comes from the cosmic microwave background, the faint glow of the infant universe. Tiny temperature variations in this radiation map the seeds of galaxies, but some patterns defy expectations. Certain large-scale anomalies like the axis of evil, a mysterious alignment of fluctuations, hint that our universe might bear scars from something older, something beyond the Big Bang. Could these be fingerprints of a prior cosmos or evidence of exotic physics we've yet to grasp? The truth is, we might be asking the wrong question. Time as we understand it may not apply before the Big Bang any more than north applies beyond the North Pole. In quantum gravity theories like loop quantum cosmology, time itself could emerge from a timeless quantum foam, meaning there was no before, just a transformation from one state to another. It's a dizzying thought that our entire experience of cause and effect, of beginnings and endings, might be a side effect of a deeper, stranger reality. So was the Big Bang the ultimate beginning or just a transition? The answer might rewrite not just cosmology, but our very notion of existence. Until then, we're left staring into the void, not with answers, but with wonder. What if every choice you've ever made, every path taken or not taken, exists simultaneously in a web of alternate realities? This isn't science fiction. It's the multiverse hypothesis, a radical idea gaining traction in modern physics. Picture the universe not as a single, lonely expanse, but as one bubble in an infinite froth of universes, each with its own unique laws, constants, and histories. Some might harbor life, others could be barren wastelands or realms where gravity repels instead of attracts. The implications are staggering not just for cosmology, but for how we understand our place in existence. The math behind this idea springs from inflation theory, which describes the universe's explosive expansion moments after the Big Bang. Cosmologist Andre Lind proposed that inflation never truly stops. It just pauses in pockets, creating isolated, bubble universes like voids in Swiss cheese. Meanwhile, quantum mechanics suggests another flavor of multiverse. Every time a particle faces multiple possible states, the universe might split into branches, each realizing one outcome. Think of Schrödinger's cat, but on a cosmic scale, not just a cat both dead and alive, but entire worlds diverging with every quantum flicker. Here's where it gets wild. The multiverse could solve two of science's greatest puzzles, fine-tuning and quantum weirdness. If infinite universes exist, then of course some would, by sheer chance, have the perfect conditions for life. We're not special, just lucky. As for quantum superposition, the many worlds interpretation argues there's no collapse of probabilities. Just you, in this universe, observing one outcome while alternate versions of you witness the rest. It's a cosmic game of choose your own adventure where every path is taken. But is this science or philosophy? Critics like physicist Paul Davies argue that untestable theories risk veering into metaphysics. Without evidence, some way to detect or interact with other universes, the multiverse remains a dazzling speculation. Yet supporters counter that it's no different from early theories of atoms or black holes, ideas once deemed outlandish until technology caught up. Some even hunt for bruises in the cosmic microwave background, anomalies that might trace collisions with neighboring universes in the cosmic foam. The debate reveals a deeper truth. The multiverse isn't just about parallel worlds. It's a mirror held up to science itself, forcing us to ask, how far can theory stretch before it snaps? Whether the answer lies in math, machines, or something beyond, one thing's certain. Reality, as we know it, might be far stranger than we ever dreamed. Imagine the universe in its earliest moments, a seething, chaotic soup of energy and forces. As it cooled, cracks might have formed in the fabric of reality itself, like flaws in a sheet of ice. These aren't just metaphors, they're cosmic strings, hypothetical relics from the birth of the cosmos, thinner than an atom but stretching across the entire observable universe. Picture them as ultra-dense threads of pure energy, remnants of symmetry breaking in the infant universe, where fundamental forces split apart like layers of an onion peeling back. If they exist, they'd be under unimaginable tension, vibrating like guitar strings plucked by the hand of creation, and their vibrations could rewrite the rules of physics as we know them. One wild possibility: cosmic strings might explain dark energy, the mysterious force accelerating the universe's expansion. As these strings wiggle and decay, they could release bursts of vacuum energy, pushing space apart like an invisible tide. Some theories even suggest they're responsible for the bizarre distribution of galaxies we see today, acting as cosmic scaffolding that guided matter into the vast webs and voids we observe. It's as if the universe left behind invisible blueprints, and we're only now learning how to read them, but the strangest ideas come from their sheer gravitational power. A cosmic string's density is so extreme that it warps space-time around it like a whirlpool. Two strings crossing each other could create closed time-like curves, theoretical pathways where time loops back on itself. In other words, they might be natural time machines, though the energy required to harness them is beyond anything we can conceive. Even more practical, relatively speaking, is the notion that advanced civilizations could tap into cosmic strings as infinite power sources, siphoning energy from the universe's own birth pangs. The catch: we've never seen one. They'd be nearly invisible, detectable only by the way their gravity bends light from distant galaxies, or by the faint ripples they'd leave in the cosmic microwave background. Some researchers speculate that cosmic strings might have already evaporated, their energy dissipated into the void. Others think they're hiding in plain sight, their subtle signatures buried in data we've yet to decode. This brings us to the next great cosmic puzzle: dark energy. If cosmic strings are the universe's forgotten scars, dark energy is its silent heartbeat, a force so pervasive it makes up 68% of everything in existence, yet we can't explain what it is or why it's pushing the cosmos apart faster every second. The connection might be deeper than we think. Perhaps dark energy isn't some exotic substance, but the echo of those primordial defects vibrating across eternity. Or maybe it's something even stranger, waiting in the shadows of our understanding. One thing's certain: the universe loves a good mystery, and we're just beginning to trace its outlines. Dark energy is the universe's best-kept secret, a force so dominant it shapes the fate of everything, yet so elusive we can't even say what it is. Picture the cosmos as a runaway train, not slowing down as you'd expect, but accelerating faster with every passing second. That's the handiwork of dark energy, pushing galaxies apart at speeds that defy gravity's pull. In the late 1990s, astronomers made a discovery that turned cosmology upside down. By measuring distant supernovae, they found the universe wasn't just expanding, it was speeding up. The culprit: an invisible something making up 68% of everything in existence, yet leaving no trace except its effect on the fabric of space itself. Gravity, the force that sculpts galaxies and binds planets to stars, should be slowing this expansion. Instead, dark energy overwhelms it like an unstoppable tide, stretching the cosmos thinner and colder with time. The end game: a big freeze, where galaxies drift so far apart that their light can never reach us, stars burn out, and the universe fades into an endless, silent dark. But here's the real mystery. Is dark energy a constant property of space itself, as Einstein's cosmological constant suggested, or a dynamic force that could change over time? Some theories propose it's the energy of the vacuum, a seething quantum foam of particles flickering in and out of existence, their collective push driving the acceleration. Others speculate it could be a new fundamental force, one we've yet to name or understand. The most unsettling possibility: dark energy might not stay gentle. If it grows stronger, it could eventually overpower not just gravity, but the very forces holding atoms together, a scenario called the Big Rip. Picture a universe where galaxies, stars, even molecules are torn apart in a final, violent instant. It's a fringe idea, but the fact that it's even plausible underscores how little we know. The James Webb Space Telescope and next-generation observatories like the Vera Rubin Observatory are hunting for clues, mapping the universe's expansion with unprecedented precision. Will they find that dark energy is constant or that its grip is tightening? One thing's certain: dark energy isn't just a cosmic footnote. It's the architect of reality's fate, the silent dictator of whether the universe ends with a whisper, a tear, or something beyond our imagination. And until we unravel its secrets, we're left staring into the void, wondering what else it's hiding. Deep in the cosmic void, something massive is tugging at our galaxy, and everything around us with the gravitational pull of 1 billion suns. Astronomers call it the Great Attractor, a mysterious region of space roughly 250 million light-years away that's dragging the Milky Way and its neighbors toward it at over 1 million miles per hour. But here's the catch: we can't see it. Our view is blocked by the thick dust and stars of the Milky Way's own galactic plane, a cosmic blind spot known as the zone of avoidance. It's like trying to spot a mountain through a blizzard. We know something colossal is out there, but the details remain frustratingly blurred. What little we've pieced together comes from peering through the haze with X-ray and infrared telescopes, which reveal hints of an enormous concentration of mass, perhaps a supercluster of galaxies thousands of times larger than our local group. But some measurements suggest even that might not be enough to explain the sheer strength of the pull. Could there be something stranger lurking in the shadows? Some theorists speculate about exotic possibilities: a dense knot of dark matter, a primordial flaw in space-time, or even a gravitational echo from a neighboring universe. The truth is, we're still mapping the currents of this cosmic river, unsure if the Great Attractor is the source or just another ripple in a much larger flow. That's where things get even more intriguing. Beyond the Great Attractor lies an even more massive structure, the Shapley Supercluster, a sprawling metropolis of galaxies 8 times farther away, which might be the true anchor of our galactic neighborhood. Together, these titans suggest we're part of a vast cosmic dance, with galaxies and superclusters moving in streams and sheets across billions of light-years. It's a humbling thought. The forces shaping our corner of the universe might be far grander and far stranger than we've yet imagined. So is the Great Attractor a destination, or just a waypoint on a journey we're only beginning to understand? Every new telescope, every breakthrough in peeling back the Milky Way's veil, brings us closer to an answer, and what we find might rewrite not just our place in the cosmos, but our understanding of gravity itself. On October 19, 2017, astronomers spotted something unprecedented: a visitor from beyond our solar system, tumbling through space at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for scout, this bizarre object defied all expectations. Unlike typical asteroids or comets, it was shaped like a cosmic cigar, nearly a quarter-mile long, but only a tenth as wide, spinning chaotically as it raced past the sun. But the real shock came when telescopes tracked its trajectory. Instead of slowing down as expected, Oumuamua accelerated, as if pushed by an unseen force. Mainstream science scrambled for explanations. The leading theory, outgassing sunlight vaporizing hidden ice beneath its surface, creating a natural thruster effect. The problem, no visible coma or tail, the usual hallmarks of a comet. Others proposed more exotic ideas. Maybe Oumuamua was a shard of a shattered planet, or a hydrogen iceberg evaporating in sunlight. Then came the bombshell hypothesis from Harvard astrophysicist Avi Loeb. What if it wasn't natural at all, but a fragment of alien technology, a light sail or derelict probe? The scientific community bristled, but the debate lingered. After all, Oumuamua's odd properties, its unusual shape, unexpected acceleration, and eerie lack of dust left room for questions. The truth is, we may never know. By the time telescopes spotted Oumuamua, it was already speeding away, too faint and fast to chase. Future interstellar visitors might hold more clues. The Vera Rubin Observatory, set to scan the entire southern sky nightly, could spot dozens of such objects in the coming years. Each one could rewrite our understanding of how common or how strange interstellar travelers really are. Which raises an even bigger question. If Oumuamua was just a cosmic oddball, what else is drifting unseen through the void? Enter rogue planets, worlds untethered to any star, wandering the galaxy like interstellar nomads. Some could be ice-covered orphans flung from young solar systems. Others might be failed stars, too small to ignite. Estimates suggest there could be billions, even trillions of them, dark and nearly invisible. A few might even harbor life, warmed by geothermal vents or thick atmospheres trapping heat. The idea isn't science fiction. In 2020, astronomers detected a rogue planet roughly the size of Earth, floating alone in the Milky Way. With no sun to illuminate it, finding others will require next-gen tools like NAS and Nancy Grace Roman Space Telescope, which could spot these dark wanderers by the way their gravity bends distant starlight. So was Oumuamua a herald of stranger things to come, a natural curiosity or a message in a bottle we weren't ready to read? The universe, it seems, loves keeping secrets, but every mystery we uncover only reveals how much more is waiting in the dark. Imagine a world with no sunrise, no sunset, just endless night, drifting alone through the freezing void between stars. These are rogue planets, the galaxy's ultimate nomads, untethered from any solar system and wandering the cosmos like cosmic orphans. And they're not rare. Current estimates suggest there could be billions, even trillions of them in the Milky Way alone, outnumbering stars by as much as 20 to 1. Some might be ice-covered wastelands, frozen to their cores. Others could hide secrets beneath their surfaces vast, dark oceans kept liquid by the faint warmth of radioactive decay or the gravitational squeezing of a moon we can't even see. How do these lonely worlds end up adrift? The most common theory is brutal, gravitational violence. Picture a young solar system, its planets still jostling for stable orbits. A close encounter with a passing star or a tug of war between gas giants could fling a smaller planet outward like a slingshot, sending it careening into interstellar space. Other rogue planets might never have had a star to begin with, forming instead from collapsing gas clouds too small to ignite nuclear fusion, destined to wander from birth. But here's the tantalizing possibility. Some of these dark worlds could be anything but dead. Take Jupiter's moon Europa with its subsurface ocean. Now imagine that ocean wrapped in an even thicker shell of ice, insulated against the cold of space. A rogue planet with similar geology might retain heat for billions of years, its hidden waters churning with hydrothermal vents. On Earth, such vents teem with life, thriving without a single photon of sunlight. Could rogue planets be galactic arcs ferrying microbial hitchhikers or even more complex life between stars? The idea isn't as far-fetched as it sounds. If life can emerge around deep-sea vents on Earth, why not in the abyssal oceans of a wandering world? Finding these cosmic drifters, though, is like searching for black cats in a coal cellar. Without a star to illuminate them, they're virtually invisible. Astronomers have to rely on tricks like gravitational microlensing, waiting for a rogue planet's gravity to briefly bend and brighten the light of a distant star as it passes in front. So far, only a handful have been confirmed this way, but projects like the Nancy Grace Roman Space Telescope promise to uncover thousands more in the coming decade. The bigger question isn't just whether rogue planets exist, it's what they mean for life's place in the universe. If even a fraction of them harbor oceans, the galaxy could be filled with hidden oases, each a potential cradle for biology. And if life can survive and spread aboard these free-floating worlds, the boundaries of habitable zones shatter. No longer tethered to the warmth of stars, life might find a way in the coldest, darkest corners of space. So the next time you look up at the night sky, remember, the real marvels might not be the stars you see, but the invisible worlds silently gliding between them. The night of August 15, 1977, was supposed to be routine, just another shift scanning the skies for Ohio State University's Big Ear radio telescope. But at 10:16 p.m., astronomer Jerry Amon spotted something that would haunt science for decades. A 72-second burst of radio waves so intense, so perfectly aligned with the frequency hydrogen emits in space, that he circled it in red ink and scrawled, "Wow." In the margin, that single word named the most tantalizing and frustrating signal in the search for extraterrestrial intelligence. It came from the direction of Sagittarius, matched predictions for an artificial interstellar broadcast, and then vanished. Despite 40 years of listening, it's never repeated. So what was it? The leading natural explanation points to a passing comet. Hydrogen clouds surrounding these icy wanderers could, in theory, emit similar frequencies. But here's the catch. The WOW signal's specific frequency, 1420 MHz, is protected by international agreement. No earthly satellites or aircraft should broadcast there, making accidental interference unlikely. And comets move slowly. The signal's rapid rise and fall suggest a compact source, not a diffuse cloud. Could it have been a one-time cosmic fluke, a maser, a neutron star's glitch, or some unknown astrophysical event? Or was it, as some still argue, a fleeting hello from a civilization that turned its transmitter our way just long enough to tease us? Modern SETI projects have upped the stakes. Breakthrough Listen, funded by Yuri Milner, now scans millions of frequencies simultaneously with AI-driven analysis, hunting for patterns even humans might miss. The Allen Telescope Array, with its dish forest in Northern California, monitors 24/7, ready to pivot toward any repeat signal. Yet silence persists, a cosmic game of Marco Polo where we're left shouting into the void. But what if we're the ones not listening correctly? The WOW signal was found in a narrowband search, focusing on a sliver of the radio spectrum. New theories suggest advanced civilizations might use broadband pulses or quantum-encoded messages, slipping past our outdated filters. Others propose we're ignoring the obvious. Why assume aliens would use radio at all? A society just a few centuries ahead of us might communicate via neutrino beams or gravitational waves, technologies we're only beginning to grasp. The real lesson of the WOW signal isn't just about aliens. It's about how easy it is to miss the extraordinary when we're looking for the expected. The universe doesn't owe us signals we can understand, only the patience to keep listening. and the humility to admit we might not yet know how to hear. In the constellation Cygnus, about 1,500 light-years away, a star named KSE 8462852, better known as Tabby's star, has been throwing scientists for a loop. Unlike any other star observed, this one flickers and dims in erratic, unpredictable patterns, sometimes dropping in brightness by up to 22% before slowly recovering. When astronomer Tabetha Boyajian first spotted these anomalies in data from NASA's Kepler Space Telescope in 2015, even the most conservative researchers found themselves whispering a tantalizing possibility. Could this be evidence of alien engineering? The most dramatic theory suggested a Dyson swarm, a colossal array of energy-harvesting structures built by an advanced civilization to encircle their star and capture its power. Imagine millions of solar panels orbiting in formation, blocking starlight in irregular clumps as they pass. It's a concept straight out of science fiction, but for a brief moment it seemed plausible. After all, natural explanations struggled to account for the star's extreme dimming. Planets, too messy, no known orbit could explain the irregular dips. A passing debris field, the dimming lasted too long and recurred too sporadically. Then came the dust. Follow-up studies revealed the star's light dimmed more at blue wavelengths than red, a telltale sign of fine particles scattering shorter wavelengths, just like Earth's atmosphere turning sunsets crimson. The leading theory now suggests a chaotic cloud of dust, possibly from a shattered planet or a swarm of comets, is responsible. But even this explanation leaves gaps. Why doesn't the dust disperse evenly? What caused such a catastrophic disruption in the first place? The mystery lingers, a reminder that the universe often defies our neatest explanations. Yet the allure of the Dyson swarm hypothesis persists, not because it's likely, but because it forces us to ask a profound question. What would a civilization capable of reshaping stars even look like? That's where the Kardashev scale comes in, a framework for classifying advanced civilizations by their energy use. A Type 1 civilization harnesses all the power of its home planet. Type 2, like the builders of a Dyson swarm, commands the energy of its star. Type 3, it would dominate an entire galaxy, where humanity sits fractionally close to Type 0. The scale humbles us. But it also sparks wonder. If such civilizations exist, how would we recognize them? The answer might lie not in their messages, but in their shadows, the subtle, staggering ways they bend the cosmos to their will. The cosmos hums with energy, stars burning, galaxies spinning, black holes devouring. But what if an intelligence could harness all that power, bending it to their will? That's the heart of the Kardashev scale, a framework dreamed up by Soviet astronomer Nikolai Kardashev in 1964 to classify civilizations not by their politics or art, but by their energy appetite. At the bottom rung, a Type 1 civilization masters every watt of its home planet, controlling weather, tapping geothermal vents, even harvesting lightning. Think global fusion reactors, orbital solar arrays, and cities glowing like fireflies under a unified power grid. Humanity, we're not even there yet. By some estimates, we're a measly Type 0.7, still guzzling fossil fuels like toddlers playing with matches. Climb higher and the scale turns staggering. A Type 2 civilization doesn't just use energy, it commands it, building megastructures around its star to siphon every photon. The classic example, a Dyson sphere, a hypothetical shell of solar collectors encasing a sun, transforming it into a cosmic power outlet. But here's the twist, a full sphere might be unstable. Instead, imagine a swarm, millions of orbiting mirrors or habitats, each angling to catch starlight. their shadows flickering across the galaxy like fireflies around a lantern. That's likely what astronomers pondered when Tabby's star dimmed erratically, its light patterns defying natural explanation. Could those dips have been the shadows of alien construction? Probably not, but the audacity of the idea lingers. A civilization so advanced, its engineering scatters light across the interstellar void. Now, stretch your imagination further. A Type 3 civilization doesn't stop at one star. It rules an entire galaxy, channeling the energy of billions. Picture a network of Dyson swarms threaded across star systems, linked by wormholes or warp highways, their communications humming in neutrinos or quantum entanglement. Their art might be written in supernova, their history encoded in pulsar beams. Some theorists argue we've already seen hints of such titans, unexplained cosmic infrared glows that could be waste heat from galactic-scale engineering, or the eerie synchrony of quasars flaring in rhythm across billions of light-years. But here's the haunting question. If these civilizations exist, why haven't we heard them? The Fermi Paradox echoes here. Maybe Type 3s transcend physical forms, uploading into quantum clouds or dark matter matrices. Or perhaps they regard us as ants beneath their notice, our radio signals as meaningless as static. There's another, darker possibility, the Great Filter. What if the leap from Type 2 to 3 is so perilous, requiring technologies that risk self-annihilation, that almost no civilization survives it? Yet the scale might not end at 3. Futurists like Michio Kaku speculate about Type 4, harnessing the energy of multiple galaxies, or even Type 5, mastering the multiverse itself. These are fantasies for now, but they frame a profound truth. Energy is the currency of the cosmos, and how a civilization spends it reveals everything. So the next time you see a strange flicker in the data, an anomaly that defies explanation, ask not just what is it, but who could have built it. The universe is old, vast, and surely inventive, and somewhere in the dark, another intelligence might be scaling the same ladder, one star at a time. When a massive star dies, it doesn't always go quietly into the night. Some collapse into neutron stars, cosmic diamonds forged in the heart of a supernova, so dense that a single sugar cube-sized chunk would weigh as much as Mount Everest. Packing more mass than our sun into a sphere barely the size of a city, these stellar corpses are nature's most extreme laboratories, bending the laws of physics until they nearly break. Step too close and their gravity would stretch you into a strand of atoms before crushing you into oblivion. But it's not just brute force that makes them fascinating. It's what they reveal about the universe's most mysterious rules. Take time itself. Near a neutron star's surface, gravity warps time so severely that a clock would tick noticeably slower than on Earth. This isn't science fiction. It's Einstein's general relativity in action, proven by watching pulsars, the rapidly spinning neutron stars that beam radiation like cosmic lighthouses. Some rotate hundreds of times per second, their precision rivaling atomic clocks. When astronomers tracked the first binary pulsar system in the 1970s, the subtle changes in their orbits revealed gravitational waves, ripples in space-time, decades before we detected them directly. These stars aren't just oddities, they're celestial stopwatches ticking out the universe's deepest rhythms. Then there's the matter, literally inside them. Crushed under pressures so immense that atoms collapse, neutron stars are thought to harbor exotic states of matter unseen on Earth. Protons and electrons fuse into neutrons, creating a superfluid sea so dense it might host nuclear pasta, a structure shaped like spaghetti or lasagna sheets, sculpted by unimaginable forces. Deeper still, some theories predict quark matter, where even neutrons break apart into their fundamental particles, swirling in a soup of pure quantum chaos. If such conditions exist, they could rewrite our understanding of particle physics, revealing phases of matter that only appear when the universe plays its most extreme hand. But the strangeness doesn't stop there. Neutron stars boast magnetic fields 1,000,000,000 times stronger than Earth's, powerful enough to rip molecules apart from 1,000 miles away. Occasionally, these magnetic monsters awaken as magnetized stellar zombies that unleash bursts of energy so violent they can fry satellites and light up the entire Milky Way for a split second. In 2004, a magnetar 50,000 light-years away temporarily ionized Earth's upper atmosphere, proving these aren't just distant curiosities. They're cosmic dragons capable of breathing fire across the galaxy. What's left to discover? Some theories suggest neutron stars might conceal even wilder secrets, like cores of dark matter or portals to strange-lit matter, a hypothetical substance that could convert anything it touches into more of itself. Others wonder if collisions between neutron stars, which spray gold and platinum across space like cosmic fireworks, might also birth microscopic black holes or hidden dimensions. Every new observation, from gravitational wave detectors to X-ray telescopes, peels back another layer of the mystery. So while neutron stars may be the remnants of dead suns, they're anything but silent tombs. They're dynamos of extreme physics, cosmic beacons pushing the boundaries of what's possible. And as we listen to their pulses and study their violent lives, we're not just learning about stars, we're decoding the universe's most unforgiving experiments, one spinning enigma at a time. Neutron stars push matter to the breaking point, but what if there's something even stranger lurking in the cosmic shadows? Enter quark stars, hypothetical objects so dense, they crush neutrons themselves into a swirling ocean of free quarks, the fundamental building blocks of all matter. Picture a neutron star's core, where pressures exceed 100 trillion times Earth's atmosphere, and protons and neutrons surrender their identities entirely. Here, quarks might roam freely in a state called quark-gluon plasma, a primordial soup last seen microseconds after the Big Bang. These aren't just theoretical oddities. Some astronomers suspect a handful of known neutron stars, like XTJ 1739-285, with its dizzying 1100 rotations per second, might actually be quark stars in disguise, their extra density hinting at physics beyond textbooks. Now dial the strangeness up further. Under such extremes, ordinary up and down quarks could transform into strange quarks, creating a new form of matter unlike anything in our universe, strange matter. This substance isn't just exotic, it might be hyperstable, more perfect than the matter composing planets and stars. If true, a single droplet of strange matter could, in theory, infect normal matter on contact, converting it into more strange matter like some cosmic chain reaction. The terrifying prospect, a strangelet, a tiny fragment of this stuff, could theoretically turn Earth into an inert, ultra-dense orb in seconds. Before panic sets in, know this: we've seen no evidence of such disasters in 13.8 billion years of cosmic history. The RIC and LHC colliders have even hunted for strangelets in high-energy collisions. So far, nothing. Yet the possibility lingers, a reminder that the universe's most extreme laboratories might still hold surprises. This isn't just about doomsday scenarios, though. Strange matter could solve cosmic riddles. Some ultra-high-energy cosmic rays, subatomic particles hurtling through space with energies 1,000,000 times beyond our best accelerators, might originate from quark stars collapsing or colliding. These particles pack so much punch, Their source has baffled scientists for decades. Could quark stars be the universe's natural particle accelerators, flinging out cosmic rays like shrapnel from a detonation? The idea gains traction when you consider that certain fleeting gamma-ray bursts, the most energetic explosions since the Big Bang, might be quark stars undergoing phase transitions, their cores crystallizing into strange matter in a cataclysmic release of energy. The hunt for these objects is a detective story written in X-rays and gravitational waves. Telescopes scan neutron stars for anomalies in their size or spin, searching for outliers too dense or too cool to fit the neutron star mold. Meanwhile, gravitational wave observatories listen for the ripples of hypothetical quark-star collisions, which would ring space-time differently than neutron-star mergers. Every new observation tightens the constraints, but the mystery endures. Whether quark stars exist or not, their hypothetical physics challenges our understanding of matter itself, pushing us to ask not just what's possible in the universe, but what's stable, and whether our reality is just one configuration in a multiverse of material possibilities. So while we've yet to definitively spot a quark star, their theoretical existence forces us to confront a humbling truth. The universe's recipe book for matter might have pages we haven't even glimpsed yet. And somewhere in the dark, a strange new form of matter could be waiting, not as a destroyer, but as a key to unlocking the cosmos' deepest secrets. Somewhere in the vast emptiness of space, invisible bullets are screaming past at nearly the speed of light particles so energetic, they carry the punch of a fastball crammed into a single atom. These are ultra-high-energy cosmic rays, nature's most powerful particle accelerators, and they're raining down on Earth with forces no human-made machine can match. In October 1991, a cosmic ray detector in Utah picked up something staggering, a single subatomic particle with the energy of a major league fastball, packed into a space smaller than an atom. Scientists called it the "oh my god" particle, and for good reason, hitting our atmosphere with 40 million times more energy than anything produced in the Large Hadron Collider. This one particle carried the kinetic equivalent of a brick dropped from waist height, condensed into a speck smaller than a proton. Where could such violence come from? The leading suspects lurk in the most chaotic corners of the cosmos. Active galactic nuclei, supermassive black holes devouring entire stars, might hurl particles to these energies in their swirling accretion disks. Colliding galaxy clusters with their trillion-degree shockwaves could act as natural particle cannons. Some theorists even speculate about cosmic strings, defects in space-time left over from the Big Bang, snapping like rubber bands and releasing bursts of unimaginable power. But here's the problem. The oh my god particle arrived with so much energy, it shouldn't exist at all. According to physics, particles this energetic should be shredded by collisions with the cosmic microwave background before reaching Earth, their energy dissipated across millions of light years. Yet here it was, defying every expectation. That leaves two unsettling possibilities. Either we're missing something fundamental about how particles travel through space, perhaps they're slipping through extra dimensions or riding cosmic magnetic highways we can't yet detect, or these rays are coming from sources much closer than we think. Some fringe theories even suggest exotic relics from the early universe, like decaying dark matter particles or primordial black holes, might be lurking in our galactic backyard, occasionally unleashing these monstrous energies. The hunt for answers spans continents. The Pierre Auger Observatory in Argentina uses 1,600 water tanks spread over 3,000 square kilometers to catch the faint afterglow of cosmic rays hitting the atmosphere. Meanwhile, space telescopes like Fermi scan for gamma rays that might trace these particles back to their origins. Every new detection tightens the noose, yet the mystery only deepens. Because if nature can accelerate particles to energies we can't begin to replicate, what else is it capable of? The universe, it seems, still holds the high-energy crown, and we're just beginning to understand the rules of the game. The cosmic microwave background, the faint afterglow of the Big Bang, should be a random tapestry, a whisper of ancient heat scattered evenly across the sky. But when scientists mapped its subtle temperature variations with satellites like Planck and WMAP, they stumbled on something unsettling. A strange, unexpected alignment nicknamed the axis of evil. Stretching across the cosmos like a phantom spine, this axis reveals a peculiar clustering of hotter and colder spots that seem to line up with our solar system's plane. The odds of this happening by chance, less than 1 in 100. It's as if the universe handed us a loaded die, and we're still trying to figure out who shook it. Some dismiss it as a statistical quirk, a cosmic mirage that will fade with better data. But the persistence of this anomaly across multiple missions has forced even skeptics to consider wilder possibilities. Could it be evidence of a pre-Big Bang structure, some imprint from an earlier universe that bled into ours? Theories like conformal cyclic cosmology suggest our cosmos might be one in an endless cycle of expansions and crunches, with each iteration leaving faint scars on the next. If true, the axis of evil might be a fingerprint from a forgotten epoch, a shadow of something older than time itself. Others propose more immediate explanations. Perhaps our local universe isn't as homogeneous as we assumed, and we're caught in a vast gravitational trough, a ripple in space-time so immense it distorts our view of the background radiation like a funhouse mirror. Or maybe dark energy, that enigmatic force accelerating the universe's expansion, isn't uniform after all, tugging at the fabric of reality in ways we've yet to grasp. The most radical idea, that the axis hints at a preferred direction in the universe, contradicting Einstein's foundational assumption that space looks the same in all directions. If proven, it would upend cosmology as we know it. What makes this more than just an academic curiosity is what it implies about the universe's fate. If the cosmos isn't as random as we thought, if hidden structures or forces are guiding its evolution, then our predictions for its end might be dangerously incomplete. The Big Freeze, the Big Rip, even the possibility of a cyclical rebirth could all hinge on understanding this anomaly. For now, the axis of evil remains one of science's great unopened letters, a message from the universe we're still learning how to read. And until we crack its code, we're left with a humbling reminder: the deeper we look, the stranger the cosmos becomes. The universe is playing a high-stakes game of tug-of-war, and the outcome will determine its ultimate fate. On one side, dark energy relentlessly pushes galaxies apart, accelerating the expansion of space itself. On the other, dark matter and gravity fight to pull everything back together in a cosmic embrace. Which force will win? The answer lies in the delicate balance between them, a balance we're only beginning to understand. Picture two possible futures. In the first, dark energy maintains its dominance, stretching space thinner and colder with each passing eon. Galaxies drift so far apart that their light can no longer bridge the gaps. Stars burn out, black holes evaporate, and the universe fades into a featureless void where even time loses meaning. This is heat death, not a dramatic explosion, but a slow, quiet descent into eternal darkness. The temperature approaches absolute zero, and all activity grinds to a halt. It's a chilling thought: the universe, once teeming with energy and life, reduced to a static sea of exhausted particles. But there's another possibility, one where gravity finally overpowers dark energy's push. Imagine the expansion slowing, halting, then reversing as galaxies begin rushing back toward each other. Space contracts, temperatures soar, and the cosmos collapses in on itself in a fiery big crunch. Matter and energy compress into an unimaginably dense singularity, perhaps triggering a new Big Bang, a rebirth from the ashes. Some theories, like conformal cyclic cosmology, suggest this cycle could repeat endlessly, with each universe giving rise to the next in an infinite loop of creation and destruction. There's a third, even stranger option, a big rip. If dark energy grows stronger over time, it could eventually overwhelm not just gravity, but the very forces holding atoms together. In this scenario, galaxies, stars, planets, and even molecules would be torn apart in a final, violent instant. The universe wouldn't just end, it would shatter. The key to these cosmic prophecies lies in the nature of dark energy itself. Is it a constant force, as Einstein's cosmological constant suggests, or could it evolve, weakening or strengthening over billions of years? Current observations, like those from the James Webb Space Telescope, aim to measure the universe's expansion with unprecedented precision, searching for clues in the light of ancient supernovae and distant quasars. What if the end isn't truly an end at all? Some models propose that a collapsing universe could rebound into a new one with different physical laws, while others speculate about baby universes budding off from black holes or quantum fluctuations in the vacuum of space. The line between death and rebirth might be thinner than we think, so when we peer into the night sky, we're not just looking at the past, we're glimpsing possible futures. The universe's fate hinges on forces we can't yet see or fully comprehend. And whether it ends in ice, fire, or something beyond our imagination, one thing is certain: the story of the cosmos is far from over. It might just be waiting to turn the page. At the intersection of quantum physics and philosophy lies a question so profound it redefines our place in the cosmos. Is consciousness more than just a byproduct of the brain? Could it be woven into the very fabric of reality? Consider the observer effect in quantum mechanics, where particles exist in a haze of probabilities until measured, as if the act of observation itself forces the universe to make a choice. This isn't just laboratory quirk. Pioneers like John von Neumann and Eugene Wigner argued that consciousness might be the ultimate collapse mechanism, the missing ingredient that transforms quantum possibilities into concrete reality. Even Einstein grappled with this, calling it spooky action at a distance, a phrase that hints at the unnerving intimacy between mind and matter. Then there's panpsychism, the radical idea that consciousness isn't exclusive to complex life, but a fundamental property of all things from stars to atoms. Think of it as the universe's hidden operating system, with even electrons possessing a whisper of subjective experience. Philosopher David Chalmers frames it provocatively. Why should consciousness emerge from non-conscious particles? Unless, of course, it was there all along. Supporters point to integrated information theory, which quantifies consciousness as a spectrum, suggesting even simple systems like photons or black holes might harbor rudimentary awareness. It's a vision of the cosmos where existence and experience are inseparable, where every particle hums with an inner life too faint for us to perceive. But what if the universe isn't just aware? What if it's self-aware? The anthropic principle suggests our cosmos seems fine-tuned for life because, well, we're here to observe it. Some theorists, like physicist Andre Linde, take this further, proposing a participatory universe where observation shapes reality across time and space. Imagine a cosmic feedback loop. The universe gives rise to minds, and those minds, in turn, give meaning to the universe. It's a dance of creation and perception, with no clear distinction between dancer and stage. As we stand at the edge of these ideas, one truth becomes undeniable. the greatest mysteries aren't just about distant galaxies or quantum particles. They're about our ability to question, to wonder, to stare into the void and see not just darkness, but a mirror reflecting the deepest enigmas of existence. Science has illuminated so much, yet the cosmos still holds cards close to its chest. And perhaps that's the most beautiful revelation of all. Not how much we've uncovered, but how much remains gloriously, tantalizingly unknown. We've traveled through the shadows of dark matter, danced around the edges of black holes, and even dared to ask if the universe itself might be alive with consciousness. From the tiniest quantum quirks to the vast, invisible scaffolding of the cosmos, every mystery we've uncovered only reveals how much more lies waiting in the dark. And isn't that the real magic of science? Not the answers we cling to, but the questions that keep us reaching. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That's the heartbeat of this journey, the thrill of peering into the unknown and finding not just puzzles but possibilities. Think of the cosmic microwave background, that ancient light from the dawn of time, still whispering secrets 13.8 billion years later. Or dark energy, an invisible force so dominant it's hurling galaxies apart, yet we can't even say what it is. These aren't just gaps in our knowledge. They're invitations to wonder, to imagine, to keep exploring. Neil deGrasse Tyson put it perfectly. The universe is under no obligation to make sense to you. And that's the beauty of it. The cosmos doesn't exist to comfort us with tidy answers. It challenges us, stretches our minds until they ache, then shows us something stranger than we ever dreamed. Whether it's the eerie silence of the Fermi Paradox or the fleeting flicker of Oumuamua, these mysteries remind us that reality is far richer, far weirder than our textbooks can contain. So here's the real takeaway. This isn't the end of the journey, it's the beginning. Every time you look up at the night sky, you're not just seeing stars, you're seeing questions. What flickers in the voids between galaxies? What hums in the quantum foam beneath our feet? The universe is a story still being written, and you're part of it. If these cosmic riddles have sparked your curiosity, hit that subscribe button because we're just getting started. From the secrets of neutron stars to the hunt for alien megastructures, there's a universe of wonders left to explore. So keep looking up, keep asking what if, and remember, the greatest discoveries don't just change what we know, they change how